In this video, we're going to talk about nuclear chemistry. What word does nuclear remind you of? Probably it reminds you of nucleus. And remember what's in the nucleus? Protons and neutrons. So when we're talking about nuclear chemistry, just picture the nucleus, because we're really talking about the changes that are happening inside an atom's nucleus. Now, previously we talked about isotopes. What is an isotope? An isotope is an atom that has different amount of neutrons, which then affects the mass number. And keep in mind that all elements have isotopes. And so in nuclear chemistry, we're talking about radioisotopes, isotopes that emit radiation. So radioisotopes are atoms with an unstable nucleus emitting radiation. When atoms have an unstable nucleus, they have all this energy built up inside that in order to let out the energy, the only way it can let it out is through radiation. I always give the example of a hot-tempered person. Now visualize that person and think about how much anger they built up inside, how much energy is being built up inside, and that when they release the energy, they might lash out at somebody or whatever it may be. What happens to the person after? Usually they calm down, right? Usually they're stable again. And that's kind of similar to these radioisotopes. They have so much energy pent up inside that they release that energy in the form of radiation, so that's a lot of energy going out. And then afterwards, their nucleus is stable, okay? Now, generally, elements with atomic numbers greater than 83 are radioisotopes, and elements with atomic numbers less than 83 have isotopes with a stable nucleus, but also have at least one radioisotope, which again means unstable nucleus emitting radiation. Now here are some examples of radioisotopes in our real world. Now we use radioisotopes in medicine. We use it for radio tracers to detect disease. We use it in PET scans. We use it to treat cancer. We use it in archaeology and geology. I'm sure all of you have heard of carbon dating. We use it in food. We zap our food with radiation to prolong the life of our food and also to get rid of some bacteria. And I'm sure all of you have taken an x-ray before, whether it's at the dentist or a doctor has taken one for you because of a broken bone. And also we have radon levels in the area. So in the US, radon just exists in our soil and rocks. A lot of us do radon testing in our homes, especially if you have a basement or if you live on the ground level. They want to make sure that radon levels are not too high. And the reason why it's a concern is because it's the #1 leading cause of lung cancer. And so we want to make sure that there aren't high levels of radon where you're living. And in Virginia, we're usually fine in our area. Here are some of the risks and benefits to radioisotopes and using radiation. Sometimes, we have to think about if the benefits outweigh the risks, right? So let's jump into what nuclear reactions are all about. So chemical reactions, which will be the focus for the rest of the year, involve a change of electrons, meaning the nucleus does not change. But here today, we are focusing on nuclear reactions, which involve a change in the nucleus, which means our protons and neutrons change. Remember that the number of protons in the nucleus determines the identity of an atom. And as these radioisotopes go through these nuclear reactions, the nucleus changes, meaning that the number of protons will also change. So what's going to happen if the number of protons change? That means the element itself will change. And we'll talk more about that later on in this video. So Henry Becquerel discovered that radioactive atoms undergo significant changes that alter their identity. Unstable nucleus lose energy by emitting radiation, and as the radioisotope tries to stabilize, it transforms into a new element. Now, Rutherford discovered the 3 different types of radiation: alpha, beta, and gamma radiation. So here's Rutherford's experiment. He has this radioactive substance inside this lead block, and these are electrically charged magnetic fields, so positive on top and negative on the bottom. And he shot the substance through, and he saw that some of the particles went up towards the positive, some of them went down towards the negative, and some of them went straight through. So what did Rutherford conclude from this? The ones that were attracted to the positive field are probably negatively charged. And that's what he called the beta particles. The ones that were attracted towards the bottom to the negative field were positively charged, and that's what we called alpha particles. And the ones that were unaffected and that went straight through said those are neutral, and those are called gamma rays. So let's take a look at each one of these particles. Now there are three types of decays that a radioisotope can go through. The first one we're going to talk about is alpha decay. In alpha decay, the nucleus emits, or it gets rid of, an alpha particle. An alpha particle has 2 protons, 2 neutrons, and a +2 charge. It is equivalent to a helium-4 nucleus, and therefore the alpha particle is actually represented by helium-4. Alpha radiation can be stopped by a sheet of paper. So you hold up a sheet of paper right up in front of your face, it can stop an alpha particle. This is an example of an alpha decay. So uranium-238 goes through alpha decay, and look at what happens to the element. First we had uranium. Do we still have uranium on the other side? No, because as uranium goes through this alpha decay, remember nuclear reaction, it means a change in the nucleus, which means change in protons and neutrons. And so uranium is not the same uranium anymore, but as it emits that radiation, it now becomes thorium. And this is how we know it went through alpha decay. It is represented by this helium-4 symbol, 4-2 helium. So the second type of radiation is called beta decay. Beta radiation consists of fast-moving electrons that have a charge of -1. It can be stopped by any thin piece of metal. An example of beta decay is the following. Here we have thorium, and it goes through beta decay, and it changes into a completely new element. And here the 0-1e is what we use to represent a beta particle. The last one we're going to talk about is gamma emission. Gamma radiation is just high energy that possess no mass and no charge. It usually accompanies alpha and beta radiation, and it accounts for most of the energy lost during the radioactive decay process. An example of gamma, for example, is X-rays. Because gamma rays are massless, gamma rays by themselves cannot form a new atom. It can be stopped by lead or concrete, which is what we see here. So you can see that alpha can be stopped by a piece of paper, beta can be stopped by a thin sheet of metal, and gamma can be stopped by concrete. So let's summarize and go ahead and fill this in your table. We have 3 particles, alpha, beta, and gamma. Alpha is represented by a helium nucleus, and go ahead and add this symbol onto your notes as well. We know that it's an alpha particle when it is represented by this symbol here. (4-2 helium. It can also be represented by this, which is just an alpha symbol. It's the Greek letter alpha. Beta are represented by electrons, 0, -1e, or it can also look like this. This is the Greek symbol for beta. Gamma, remember, has no mass, no charge, and that's the symbol for gamma. It's like a diving fish or an upside down ribbon. Now we're going to take a look at some of the nuclear equations and nuclear reactions, and again go through how we can identify these nuclear equations as alpha, beta, and gamma decay. So let's go through alpha decay. Here we see polonium, and it's written like an isotope. Polonium-210 is the mass number, 84 is the atomic number. It goes through and emits an alpha particle, and it goes through an alpha decay. And again, this is how we know that it's an alpha particle. And notice that the new element that is formed is lead. So now we have lead-206, right? Polonium, as it releases that alpha particle, becomes a new element, and that is lead. Beta decay, here we have carbon, and it releases the beta particle. Here we have a new element, nitrogen-14. Last one, gamma emission, here we have uranium. It goes through a type of decay, and we have our new element, thorium-234. And notice that this is the gamma symbol here, so that's how we know it's gamma. But notice that it is also being followed by alpha decay, and we know that because of this 4,2 helium symbol. So you do have to recognize these symbols here. Know that 4,2 helium is alpha, 0 minus 1 E is beta, and 0, 0 with the fancy looking Y is gamma. So let's take a look at this example. It says balance the following nuclear equations and indicate the type of decay. So in order to do this example, here's what you do. We're going to take the top numbers separately from the bottom numbers. The arrow is going to be represented as an equal sign. And if we see a plus, we're going to go ahead and put a plus in our equation as well. Here, this is our blank. Okay, so we'll put the top part as x and the bottom part as y because these are the two things that we need to find. Okay, so we're going to start with our top numbers, and I'll write it to the side over here, 222, and I'm going to go ahead and ignore the element symbols. The next part is equals because of that arrow sign. We have a blank, so that's x plus 4. So what is x? Subtract 4 on each side, and x is equal to 218. So I'm going to go ahead and write the 218 in the top part of this blank space. So I'm going to go ahead and write 218 here. And now I'm going to take a look at my bottom numbers, 86, this one, and this one. And I'll write it over here. 86 is equal to y plus 2. So what is y? Y is equal to 84. 84 in here. And now what I do in order to find the symbol or the element is I have to look at my atomic number, which is the 84. So I look at the periodic table, find 84 and 84 is polonium. So I'm going to go ahead and write the symbol P, capital P, lowercase o. And so my answer is polonium-218, which is the new element that's being formed. And what type of decay is this going through? This is going through alpha decay. Let's go and do our second example. We're going to do the same thing. We're going to take the top numbers. Remember, the arrow represents an equal sign. Here we have a plus sign over here. So we're going to take the top number, say 7 is equal to 7 plus x. Well, what's x? X is 0. Now let's take a look at the bottom numbers. 4 is equal to 4 plus y. So what is y? Y is also equal to 0. Well, what do you recognize as 0, 0 that we learned today? 0, 0 is gamma. So I'm going to go ahead and write the gamma symbol here. And this is going through gamma. Notice that you can always double check your work. Okay, so the right side has to equal the left side. So 7 plus 0 is equal to 7. 4 plus 0 is equal to 4. That's perfect. On the top example, 218 plus 4 is equal to 222. 84 plus 2 is equal to 86. We are 100% correct.